So let's begin with lecture 8 of our course on astronomical data analysis using Python. Before we get going with today's lecture, I'd just like to inform all of you that assignment 2 has been prepared by Pritish, and we should soon be uploading, probably tonight or tomorrow morning. The assignment will get uploaded on the Moodle site, and so please start looking at it. We have not yet decided when we will have the tutorial session for the second assignment, but it will certainly not be before the Thursday of next week. Okay, so you will have time to go through the assignment. This assignment is somewhat more difficult than the previous one, and certainly it's very different because for the first time you are going to be asked to work with astronomical catalogs and images, and the assignment will require you to read in data, read in images, process them in certain ways, and write them out. So there's plenty to look forward to there. So I hope you do the assignments. Unlike the previous assignment, which for a proficient programmer was just a few minutes of effort, this assignment will require you to spend time. So I expect that before the tutorial happens, all of you will give your best in trying to solve the questions in these assignments, in the second assignment. So let's get started. Before we get into more of numerical Python, I just wanted to tell you that the slice that I am taking through numerical computing in Python is a very, very narrow slice. And that's the slice that will take us towards data analysis. But if you do other things, other kinds of numerical computing, you will find that many of these modules listed here are of some benefit. NumPy, we've looked at already. Scipy is something that I will briefly discuss in this lecture. Matplotlib, we have looked at in the last lecture. And I mentioned that there are other plotting packages. For example, GNU-plotpy has SM and pgplot. All of these have nice interfaces to Python. So if you are very proficient in, say, GNU-plot, and you would prefer to use that instead of Matplotlib, that option remains open to you. Then there is something called MathLink, which provides an interface to Mathematica. So if you use Mathematica in your work and you need Python to talk to your Mathematica server, then that can be achieved via the MathLink module. It basically allows you to communicate both ways, send data from Python to Mathematica, do some processing there, pull the data back, do some more processing in Python, and so on. Similar to Mathematica is a new module, or not so new module in Python called SymPy. And SymPy is a Python module for symbolic computation. And those of you who have used Mathematica will understand immediately what I'm talking about. It's where you don't do all calculations numerically as are usually done on a computer. You retain them as symbols. Okay, so for example, you can write tan inverse 1. Okay. And then that will be retained as a value, and you'll get it in terms of pi and so on. So everything is done symbolically. It's not evaluated explicitly unless you ask it to be evaluated. So SymPy is, of course, not at the moment as capable as Mathematica, but it is improving all the time. Then there is a piece of software called Mayavi. It's a module which allows you to do 3D visualization using VTK. That is something that is also potentially useful, especially if you have a lot of numerical simulations that you want to visualize in 3D. then Mayavi is an option to look at. Pymat is the Python MATLAB interface that allows you to connect to MATLAB programs. And PyTave similarly is the Python GNU Octave interface. You must remember that that some of these softwares, such as MATLAB and Mathematica, are licensed softwares. So you have to have a properly licensed version of the software running on your computer before you can exchange data with Python. So that assumption is always there. But there are others like GNU Octave, which are free software. So you don't have to worry about a license and things like that. R is a very, very powerful statistical programming language, and it is very rich in statistical routines. So if you're really a statistician, you would obviously know R. And then if you need to exchange data with Python, you would use RPy, which is Python's R interface. And then in recent years, there is a very, very ambitious project which has started, which is called SageMath. And it aims very ambitiously to provide an alternative to all of these four popular softwares, which are Magma, Maple, Mathematica, and MATLAB, which are very widely used internationally and are very popular. SageMath, given its sort of ambitious aims, is obviously going to take a long time before it reaches the same level of maturity as these other commercially available softwares, which have been around for decades. And so it'll take time, but already you can see a lot of interesting developments happening with SageMath and so on. So I've mentioned all of these possibilities, symbolic computation and things like SageMath and interfacing with R, just to give you a flavor that we're going to not cover most of these things, to make you understand that what we are doing is a very, very tiny portion of the Python third-party module landscape, which is really very vast. You can do many, many things with Python, and people are doing those. But in order to do that, you have to familiarize yourself with the right modules and the right functions and methods within those modules. So it's a very, very long journey. We are not going to do that. Our course is a very short course, which will cover only the essentials that we really need for our purposes. So one of the things that is very popular in the numerical Python community is a module called Scipy. And what is Scipy? Scipy is a module that is very, very closely allied to NumPy. In fact, Scipy uses NumPy arrays as their building blocks for all computation. But what does it? Why is it a separate package from NumPy? Early on, it was felt that NumPy should just do the core functionality that you need of a package. Okay, so NumPy, for example, doesn't allow you to make plots like Matplotlib does. Okay, it doesn't allow you any advanced numerical computation capability. But all of that has been pulled out of NumPy and made into a separate package called Scipy. Okay. Now, Scipy itself contains a very large number of submodules. Okay. And I have listed them here. I will not go through each of them, except to draw your attention to a few of them, which I myself have found very useful. So FFT pack, for example, is very useful if you do astronomy that involves Fourier transforms. This may be in radio astronomy, but there are also people in cosmology who study the power spectrum of galaxies and so on. They also would find the Fourier transform capabilities of FFT pack very useful. Integrate is good if you need to do some numerical integration. The interpolate function is very, very widely used in all kinds of data analysis. So if you have some data to which you need to fit a spline, that can be done quite easily using the methods in the interpolate module. Then there is something called ND image, which allows you to do n-dimensional image processing. You can have not just 2D images, but data cubes. So for example, in astronomy, it's common to have, when you do resolved spectroscopy, to have a spectrum at each point on the sky, so that the lambda, the wavelength axis, becomes the third axis, and your data, instead of being a function of x and y, becomes a function of x, y, and lambda. So all of that n-dimensional image processing can be done with ND image. Optimize is also a very, very useful module within Scipy, and it includes a large number of optimization algorithms. I'm going to point you to some of the methods within this module, which I found to be very useful. If you do a lot of 1D signal processing, then the signal processing tools in Scipy are also worth a look. Special functions capability is there. The capability to handle matrices of various kinds is there. And last but not the least, there is a package called scipy.stats, which contains a very, very large amount of statistical functionality. So for example, if you want a distribution of some kind, a chi-square distribution or Poisson distribution or some other distribution, or if you want to do some tests like the Kolmogorov-Smirnov test or any other statistical tests, Anderson-Darling test, and so on, all of those can be done from within Scipy via this stats package of Scipy. Scipy, needless to say, is a much larger package than NumPy. So if you've downloaded NumPy and you've downloaded Scipy, you'll find Scipy takes much longer to download than NumPy does, because it's a much larger package. If the statistical functionality within scipy.stats does not meet your requirements, then you probably need to go to R, and R being a specialized software for statistical work, it has basically everything. So via RPy, the interface module between R and Python, Scipy can interface to R, and then you'll be able to use the statistical functionality from within the R package. So curve fitting is something that we often need to do, okay? And astronomers do it all the time. And one of the more useful functions for doing that is scipy.optimize.curveFit. And the algorithm that it uses is called the Levenberg-Marquardt algorithm. And it does what is called as a least square fit. And you can pass additional keyword arguments to that algorithm. And it's a quick and easy way to fit an arbitrary function to some XY data, right? So if you have some data and you want to fit a parabola to it, or you want to fit a straight line to it or something else, then consider using this function, okay? This function is very, very fast because the Levenberg-Marquardt algorithm that it uses is known to be extremely quick in converging. But if you have a very, very complicated curve that you need to fit, or if you need to fit curves in higher dimensions, then this will not work for you, and you'll have to go for some more sophisticated algorithm, which you would likely find in this function, scipy.optimize.minimize. And this is generally something that astronomers again often do, which is they have some data and they have some model which makes predictions about what the data should show you, and you want to match or fit the predictions of the model to the data itself. And the data might be over many dimensions, so you need to do a best fit over multiple dimensions, multiple free parameters. And there are a number of very, very complicated, but very, very efficient and effective algorithms that are available in the literature. And what the Scipy developers have done, that they have implemented within scipy.optimize a number of these algorithms. And there's some of them are listed here, like Nelder-Mead, Powell, simulated annealing, and so on. Scipy and NumPy are very, very well documented. If you go to this website, docs.scipy.org, you will find a large number of user guides, reference guides, developer guides, and so on. In the spirit that we used when we looked at Matplotlib, wherein we first looked at the gallery to look for examples of interesting plots, so the Scipy community has prepared what is called the Scipy cookbook, which contains a number of recipes, ready-made codes for doing very, very common tasks. Some of the tasks for which code is available are introductory in nature, while some of the others are quite advanced. So just like I told you while studying Matplotlib, just go through the gallery and see if a plot is very close to something that you need. Use that code, modify that code, and then get things exactly the way you want. You can follow a similar strategy by looking through the recipes that are there in the Scipy cookbook. See whether there is stuff there that meets your needs. And then if it does, please go ahead and use it. Of course, you'll need to modify it to tailor it to your exact requirements. While I was introducing Python to you in the first lecture, I resisted the urge to recommend books to you. And the reason for that was pretty obvious. As I told you, there are now more than 10,000 books available on Python programming. And many of these are basic beginner books, but I am in no position to recommend to you anything specific, because literally hundreds of them are quite good. So it is really a matter of your learning style and your preferences. So I urged you to go find books what you like, but you don't really need books for the basics of Python, because there is a lot of material available online, both in the form of user guides, but also in the form of courses and training videos for basic Python. Once you come to more advanced Python, the situation changes somewhat. The number of books that are available drops drastically. And therefore, I have decided to go ahead and make some recommendations for books that I have personally found useful in the past. So here's a list of 5 books. The first one, Numerical Python by Robert Johansson, covers much of the same ground that we have covered in our lectures on NumPy and Scipy and Matplotlib and so on. It's a very nice book if you want to learn numerical computing with Python. Then this is a good sort of beginner to medium level book. For more advanced programmers, there is a nice book called Programming for Computations, Python, by Linge and Langtangen. Hans-Peter Langtangen is a legendary author of advanced Python textbooks for science and engineering. He has written a number of them, and this one is his last and most recent one. He unfortunately passed away a few years ago. But that's a nice book. I learned much of my advanced Python programming skills by studying earlier versions of this particular book. Fluent Python is also a very nice book. It's very advanced. It tells you things that you don't usually find in any other Python textbook. Okay, so if you want to understand the innards of Python, if you want to understand the philosophy behind why Python behaves in a certain way in certain situations, then Fluent Python is a very nice book for you to read. Last year, there was a new book published, which is called Numerical Python in Astronomy and Astrophysics. This book basically is tailored towards what astronomers need. So things like fitting curves, analyzing images, analyzing spectra, and things like that are covered with lots and lots of real life examples using data that is available in the various data archives. So if you want some guidance on how you can use Python for astronomical data analysis, then this is a book to look at. Python for Data Analysis by William McKinney is another excellent book. This person, McKinney, is the lead developer for Pandas, which is one of the main modules, Pandas data frames, which are used for data analysis within Python. We have not used Pandas, but if you in your work need to use Pandas, then by all means, this is one of the best books on Pandas that's available. As always, please remember to get the most recent editions of these books. Some of the older books were written with Python 2 in mind. Now there is, as I've said since my first lecture, there is no real reason to stick to Python 2. You should all be moving to Python 3. And if they're older codes, they should be migrated as rapidly as possible. So therefore, I strongly recommend all of you to use the most recent edition of these books. Okay, so beyond this point, now we make a transition. Up to this point, everything that we have studied and learned was useful to anyone who wanted to use Python for any kind of numerical work in any domain. We've done astronomy specific things so far at all. But from this point onwards, for the 2.5 lectures that I have left, we are going to spend time almost exclusively in the domain of astronomy, where we are going to see how Python can be applied to astronomical data and its analysis. Okay, so a few years ago, the situation was really messy. There were several independent developers developing specific tools for astronomers in Python. There was a fairly large effort called PyFits, which was to enable Python to handle FITS files. FITS stands for the Flexible Image Transport System, and it is the format in which astronomical data is most commonly stored. It's a very well-defined standard, and it guarantees that a FITS file written in one location will be readable by the FITS reader software at another location. Intercompatibility has been guaranteed by defining a world standard which has been adopted, not just for images and spectra and data cubes and so on, but also for tables, also for catalogs of astronomical sources. So, PyFits was a large effort. At the same time, there was another effort called PyWCS, which enabled world coordinate system transformations, converting from sky coordinates to pixel coordinates and vice versa. All of that was there in PyWCS. Astronomers needed to handle tables of all kinds. Sometimes they were ASCII tables, sometimes they were not fixed tables. And therefore, in that situation, there was a module called AddPy and another called ASCII table that allowed you to handle tables. There were various cosmological calculators that were available. There were tools for coordinate transformation, for example, converting from one epoch to another, or converting from, say, galactic coordinates to equatorial coordinates. There were tools that allowed you to do that, and many more things that astronomers need as part of their work. However, there was a big problem with this. That one was there were different programming styles. So, for example, some of them supported object-oriented programming very well, while others were very, very functional programming oriented. There were lots of repeated efforts, the same functionality. Okay, for example, finding the luminosity distance, knowing the cosmology and the redshift was there in many packages. There was no coordination. Some of the packages had bugs. And those bugs were never found because there were so many packages that each package had a very limited number of users, and therefore we never knew that there was a bug in the code. Lots and lots of chaos and confusion. Finally, people said, no, this cannot continue. We are in deep trouble if we do this. Python will never succeed in becoming an important tool for doing astronomy data analysis if we continue like this. And the solution, therefore, was a module, to build a new module called Astropy, and to unite all of these efforts under one roof, under one banner. And that was done about, this work on Astropy started, I think, about a decade ago, and it has really matured in recent years and become a very, very powerful and efficient module for doing astronomy in Python. The website is www.astropy.org, very nicely organized website with lots of information. I point you to the Astropy tutorials on the website. These form excellent resources to learn Astropy from. Astropy has developed rapidly over the last 5 or 6 years. Version 5 of Astropy was released just last week. Okay. Astropy has now grown to such a size that it has become important to make that NumPy, SciPy kind of slicing within the package. So what we have now in Astropy is something known as the core package. So just like NumPy provides only the core functionality for numerical computing in Python, and SciPy provides much of the rest. Similarly, the core package of Astropy defines and provides the basic functionality, and then add-on things are outside it. There are two kinds of packages outside the core. The first are what are called coordinated packages. These are packages whose development is influenced or controlled or coordinated by the Astropy core developers. Okay. So for example, what does this mean? This means that if there is a change board or a group of core developers that are developing a package, for example, AstroQuery, then that group also has representatives from the core Astropy developers. And this is to ensure that any new code that enters one of these coordinated packages is consistent with the overall architecture of the Astropy module. Okay, and there are at the moment 8 such coordinated packages. AstroPy Core itself is one of them. AstroQuery is another. AstroQuery is a module that we will look at in one of the future lectures, and it's a really powerful way of basically getting data from the internet, from within your program, even running searches on the internet and downloading the search results automatically and so on. Given this powerful functionality, it was felt that it should be a coordinated package, and therefore it is there. In addition to that, there are something known as affiliated packages of AstroPy, and I've listed some of them here. APLPy, as I mentioned in my lecture on Matplotlib, is something that uses Matplotlib to make professional publication quality figures for astronomical data. GalPy is another module which does galaxy dynamics. AstroML is a machine learning library for astronomy. SynFot is a module that does synthetic photometry, and so on. The number of affiliated packages is quite large. There are 44 packages that were listed on the AstroPy website as of today. And depending on your interests, you will need to use one or more of these packages. So depending on what kind of data analysis you're trying to do, you need to download and use one or more of these packages. Why are these packages called affiliated? They're affiliated because they agree to follow the core design architecture of AstroPy, make sure that they are compatible with core AstroPy as well as with other modules, other affiliated packages in the AstroPy ecosystem. So quite important, but not as closely controlled by the AstroPy core group as the coordinated packages are, right? AstroPy has grown into really a worldwide community project. People have realized the value of AstroPy, and many developers across the world are now funded to add functionality to the AstroPy ecosystem. And this is happening literally all over the world. So AstroPy has grown to be the premier astronomy module in Python, and its capabilities will only increase dramatically in the near future. Okay, so what does AstroPy contain? Okay, so first of all, it defines a large number of data structures and transformations that are unique to astronomy. Okay, so it defines astropy.constants. So for example, astronomers use the Hubble constant to measure the rate of expansion of the universe. Nobody else uses it. So that is defined in astropy.constants. You will see that there is a parallel between many of the packages that we saw in Scipy and their equivalents in AstroPy. And the philosophy in AstroPy has been to not repeat what has already been defined in Scipy. So in Scipy.constants, you will find other physics constants like the speed of light or Newton's constant and so on defined there. These are not again defined within AstroPy, but the astronomy specific constants are definitely defined here. Units and quantities, this is very important because the moment you define a constant, many of those constants come with their own units, and you should be able to do a computation by manipulating the units of the various variables that you have. N-dimensional data sets are handled in astropy.nd-data. Data tables are handled in astropy.table. Time and dates are handled in astropy.time. Time series, for example, there are now people who study transients of various kinds. who need to measure the flux as a function of time and then do the analysis on that. That's called as a time series. An AstroPy.time series module has a number of functions that allow you to work with time series data. AstroPy.coordinates is something that allows you to transform from one coordinate system to another. AstroPy.wcs is something that allows you to modify and construct the world coordinate system that defines a mapping from the pixels that you have in individual images to their position on the sky. Models and fitting, there's a lot of optimization, minimization possible within Scipy, as we saw a few minutes ago, but AstroPy.modeling allows you to do all kinds of models and fitting, which are very common in the astronomical context. AstroPy.uncertainty allows you to handle uncertainty, errors, and so on. For file input, output, and communication, again, AstroPy has a number of sub-packages or sub-modules. It provides a unified file read and write interface. For handling fits files, okay, it contains astropy.io.fits, which we are going to encounter a bit later. And it also includes astropy.table for handling ASCII tables. Astropy.io.ascii is another module that provides functionality, but as we shall see, astropy.table provides you a sort of higher level functionality and is easier to use. There was and is a very large effort in astronomy called the Virtual Observatory, which aims to define a set of interoperable standards to allow for smooth exchange of astronomical data between large data sets lying on different computers and servers across the world. So they have defined their own data format, their own table format. They call it VO table for Virtual Observatory table. It's basically an XML-based format. So that if you want to use files using that format, then use astropy.io.vo table. Then there are miscellaneous other formats in which you may encounter data occasionally. As I said, much of the data in astronomy will be in the form of fits data. Some of it may be in ASCII tables, some of it may be in VO tables, but much of it is going to be fits. But occasionally you will encounter other formats which you will have to use. Then in the Virtual Observatory, it also talks of the ability to exchange data between different kinds of Virtual Observatory compatible applications. And that is done using a protocol called SAM, the Simple Application Messaging Protocol. And if you want to use SAMP-enabled tools from within a Python program, then astroby.sam is where you have to head. Cosmological calculations are very important in astronomy, even for astronomers who don't do cosmology. They need to convert, for example, to convert their the measured flux into a luminosity of a distant galaxy. They need to know the luminosity distance and so on. All of those functionalities are encapsulated in the astropy.cosmology module, which we are going to look at a little bit in this course. Convolution is something that happens all the time, intentionally or unintentionally in astronomy. Astropy.convolution is the place to go for this functionality. Astropy.visualization provides some tools for visualizing data. And astropy.stats provides a few things that are not already available in this very, very large and capable scipy.stats module that I mentioned earlier. Okay, so what are we going to cover in Astropy? So in the first part of our coverage of Astropy, we are going to look at table management features and handling of fits images. Okay, we look at data cubes, 3D data cubes also, very likely in the next lecture. We look at cosmological calculators. We can look at how WCS, World Coordinate System, changes and transforms are applied within the Astropy module. Okay, so the most common thing that astronomers encounter are catalogs or tables of giving information of objects of various kinds. The table management in Python is done via a table submodule, which is located inside Astropy. Okay, so before we start looking at astropy.table, a little bit about astropy.io.ascii versus astropy.table. Astropy.io.ascii is meant purely for reading and writing tables. Okay, it's a collection of extensible classes which can be extended to support newer formats. So if some new format for storing a data table appears, astropy.ascii can add some extra functionality to allow you to read that table. Astropy.table, on the other hand, is something that is built on top of astropy.io.ascii and uses its functionality for reading and writing tables and by adding its own powerful table operations. You will find that astropy.io.ascii is something that you will not need to study in great detail unless your tables have some special features that require you to go to the lower level functionality of astropy.io.ascii. Okay, so now we've talked of object-oriented programming and objects very often in this course. But what you need to understand is that objects are really instances of what is called a class. Okay, so what is a class? A class is something that defines an object. So we know that objects have some very well-defined behavior. Okay, so for example, if there are two strings, if I put the plus operator between the two strings, those strings will get concatenated, right? If I try to multiply two strings, on the other hand, that is an operation that's not defined. Okay, so it cannot be done. So what is a class? It's a class that basically defines the properties of all the objects within that class. So it tells you that if you have string objects, you can concatenate them, but you can't multiply them, right? It tells you what are the supported operations on these class of objects. Now, in order to define what operations are supported and what are not, the rules need to be defined somewhere. And a class is very, very crudely put, is a definition that allows you to create objects of a certain kind. So we have created integer objects, we have created figure objects, we have created this string objects, and so on. To create table objects, we need to instantiate or create an object of the table class. So let's begin. First, we need the table class to create these table objects. From Astropy import table. Sometimes you get a warning, but just ignore the warning. In this case, for example, in this version of Astropy, I did not get a warning. Next, we need to create the table object using a file. So I had created a small file called demo.txt. It's an ASCII text file with some data in it. And in order to load the data or read the data from the file that's sitting on disk, I just do this. Demo table is equal to table.read, give the name of the file, and specify the format is ASCII, right? Moment I do that, that table is read. Of course, it doesn't print anything because there's nothing to print. What if the table does not load? Sometimes if you get errors, it means your file is formatted in a way that the standard parser is unable to understand the structure of your file. So if your file is not very regular, it doesn't have fixed columns and so on, then it can get confused. Or if it has some special characters, the parser can get confused. So what to do? Then you have to use the lower level functionality available in astropy.io.ascii and use the read method there and supply those options, various options to table.read. Okay. So for example, you may say that header start is equal to semicolon. So if a particular row belongs to the header, then it will start with a semicolon. The delimiter between various columns may be a pipe symbol. All of this is something that you can specify while reading the file. Okay. So what do we do next? We want to display the table. We just say print demo table. Okay. We've already read the thing into a file. So what is this demo table? Is it a NumPy array? No, it's not a NumPy array. It's a table object. Okay. So think of it as a table object, and the table object itself will be composed of various sub objects, some of which may be NumPy arrays. Okay. So please don't think of the table as a NumPy array. You can convert it into a NumPy array if you want, but by itself, it's not a NumPy array. It's a object of the table class. Okay, so when we printed it, it printed 5 columns. So it seems to be their names of galaxies, the date on which they were observed, and what is their B band and V band magnitude. Okay, these are dummy numbers, they're not real. So for example, M31 is the Andromeda galaxy. It's much brighter than the number that you see here. But let us, for demonstration purposes, just say that, fine, we've read in some data, okay, from a file. I'm going to share the demo.txt file with you on Moodle, so you'll be able to look at the exact structure of that file. You can do demo.table.pprint. This pprint is a function called prettyprint. In this case, it prints exactly what was printed on the previous slide. But here you can supply options like the maximum number of lines you want to print, the weight, and so on, and whether you want to show the name or not. So here's when we print it with show name equal to false, we pprint it. And what has happened with respect to the previous attempt, this particular line, which gave the names of the various columns, and that second line with dashes has been removed. And you're just shown the raw data if it were. There are more ways to print tables in astropy.table. Many of you who have used Unix will be familiar with the more command in Unix. Basically shows you data one screen full at a time. So it's an interactive table scrolling tool. Demo table.more will give you that functionality. If for some reason you want to display it as a formatted table within a browser, demo table.show in browser basically takes your table object, converts it into an HTML table, opens a browser, and shows you the table within that browser window. You can quickly check the basic properties of the table, loaded table. So there is a concept of a length of a table, and that basically corresponds to the number of rows of data that you have in the table. So if I do print len demo table, it prints the number of rows. If I print demo table.call names, then it prints the names of the various columns. So we saw name, observation date, magnitude in the B band, and so on. If there is some metadata about the table which describes the properties of the table itself, then demo table.meta will print that out. If you want to access specific columns of a table, this is how you do it. Print demo table name. Okay. And what is name? Name is the name of the column. In this case, the name of the galaxy that you want to select, or that you want to print out in this case. So this will only print the name column of your table. If you want to print more than one column, that is also quite straightforward. And this is how you would do it. So what you do is print demo table and give a list. Okay. Give a comma separated list of columns. Okay. And you can print 1, 2, 3, any, right? You can even print them in any order you want. So you could print column 1, then print column 5, then print column 4, and so on. All of that is possible. If you want to access specific rows in a table, you would use the index directly, the numerical index. So columns are always indexed like they were a dictionary, like you would access the entries in a dictionary. And so you access it by specifying the key that you are interested in. In the case of rows, you just access it the regular way, where the 0th row is the first row, and so on. And then it just prints out for you. It prints out the header, and then it prints out the demo table. Lines. So there is another function called pformat, which basically returns everything as a list of strings. Each string is a row, and it unfortunately or unfortunately includes the header. Okay. So in order here to get the first line, you have to do print lines 2, because the first line is the header column name. The second line is those line of dashes and so on. You can access individual elements, okay, in this way or this way. So demo table name 0 means give me the name of the object which is in the first row, 0th row. Okay, and then print M31. You can also do demo table 0 name, which also works the same way, because then this will return for you the first row, and this square bracket will return the name entry for that specific row. You can do subsectioning of tables. So very often nowadays, if you download a table from a large astronomical survey, for example, in the Sloan Digital Sky Survey, some of the image catalog tables can have 600 columns. Okay, so it gets downloaded from the internet, but you are really interested in maybe 2, 3 of those columns. So you can create a subsection column in this way by specifying any number of columns that you're interested in via their names. If you want specific rows to be picked up, you can make a slice like this. So start with 0, 1, 2 row, which means the third row, and show me the third, fourth, and fifth rows. Okay, remember indexing starts with 0 in Python. You can specify the subsection of the row in another way by giving it a list as input. You can also do a cut by specifying specific rows and columns. Okay, so this will return for you only the name column and the MACB column, and only for this range of rows. Okay, so you need to change elements inside a table. Okay, now you know how to access columns, rows, and individual elements. So just like NumPy arrays and so on, these are mutable objects. A table is a mutable object, and therefore the entry in a table can be changed directly. Okay, so using the equal to sign, you can therefore assign the selected row, column, or element to another value. Okay, so demo table name will give you a list of 10 names. And if you set demo table name to single name, okay, that also works. So you can give it, rename all the 10 names, or you can give it all a single name. So let us look at an example. So we've printed out our demo table, and now we say demo table name is equal to X. So we have assigned a value capital X to name. And since we haven't specified which rows we want to affect, it'll affect all the rows, right? And so now what has happened, all that M31, etc., M82, etc. has disappeared, and you are left with X as the name of the demo table, right? You can add a new column, okay? So you can say the demo table new column is equal to range len demo table. So it will give you numbers from 0 to 9, okay? And then you can print the demo table. It adds in this column. There has been a mistake in preparing this slide. Actually, there is another way of adding columns, okay, using the column object. So I actually ran this cell before I should have, and therefore this second column name has gotten added. But don't worry, that is, I'll show you now where that comes from, okay. So you can also use using a column object. So just like the table itself is an object, every column is a column object, every row is a row object, and so on. From astropy.table, you import column. New call is equal to column data range length demo table. So basically numbers from 0 through 9, and you give it a name, okay. And then you say that demo table.add column new call index equal to 0, which means you want to add it as the first column. Now, if I print demo table, that adds in a column over here, okay, and that's the column that got mistakenly added over here. So this is just an artifact of running cells in the wrong order. Don't worry about it. Sometimes it'll happen to you in a Jupyter notebook. So just be cautious. Now, suppose you want to remove columns from an Astropy table. That's easy as well. There is a method called remove columns. And there again, you can give a list. Okay, you need not specify one column to delete. You can remove any number of columns. So the 2 extra columns that we have that we had added, we have now removed via this function. For rows, similar functionality exists. Okay, so please read the documentation of astropy.table or explore using IPython or Jupyter notebooks. You can see that you can do things like remove row 5, or you can give it a list 5, 6 will remove 2 rows, and this will remove a slice, okay, a range of rows will be removed. You can sort tables pretty easily using the sort method, which we will encounter in the next slide. So just because we have changed all the columns and rows, etc., we've reread the table again here, and we printed it. So this is our original table as it exists on the disk file. Remember, we haven't yet written out any table. So everything is just happening. All changes are happening in memory. Demo table sort is very easy. It basically takes any number of column names in a list. And what this says is that sort by the name of the galaxy and then by its magnitude. Okay. And so I printed it, the demo table, right? And again, yeah, this is again wrong because I've not run the cells correctly. I'm sorry. When I give you the IPython notebook, I'll make sure it's run correctly. But what this will do is that it will group things by name, and then it will, the secondary sort key will be the date. So it will be sorted by name and it will be sorted by date. This one just reverses the order of the table. So it reverses all the rows in the table. So the first row becomes the last row and the last row becomes the first row. Okay, so the hour is over. So I'm going to stop at this point and take your questions. We're going to cover Astropy in greater detail in the next class. So much of the next lecture will be taken up by Astropy. And in the last lecture, we will focus mostly on AstroQuery and how data can be downloaded, accessed from archives, and then analyzed.
Good evening, sir. Sir, I'm just curious, is there any method in Astrophy which will allow the user to read a table from, say, a spreadsheet or like a CSV file? Is it possible? Just like Pandas does.
Yes. So absolutely. Yeah. So there's no problem. I think it is CSVs are definitely possible. I don't know whether you can read it from, let's say, Excel.xlsx kind of format. But if you can take your Excel spreadsheet and export it as a CSV, then the CSV can be read. I believe, I'm not sure, we need to check, but I believe that astropy.io.ascii has a method for reading in CSV files, if I remember correctly. I haven't read a CSV file in a long time, so I'm not absolutely sure, but check that.
Okay. Thank you, sir.
Like NumPy also, NumPy.load text can do a CSV import quite easily also. But Astropy also has that functionality.
How can, let's say, from a fits table, we make another fits table with some of its properties, and we want to change in the header of the, we want to change some things in the header of the fits table, or say a fits image. How can we do it from Astropy package?
Yes, so I will be covering that in the next lecture. We look at how headers can be read and how headers can be modified, both for tables as well as for images. Okay. So for example, here you could easily delete a column or you could rename a column and so on. And then you could change the data in the table and then write out a table. We haven't yet written out the table that we have read in, but that will come early on in the next class. So there will be that functionality, absolutely. And updating the fits image header, that also will be covered in the next class.
Sir, you have used the word parser. I'm just curious, what does this parser exactly mean? Parsing, what does it mean really?
Yes. Okay, so parsing means like suppose I give you a row of a string with many words in it, right? A parser may try to break it up into various words and interpret that separately. So for example, when the line is read by astropy.table, It just sees some sequence of letters and numbers. Okay. So for example, when this file got read, Python saw M101 space something, something, something. Now, the parser is the thing that intelligently interprets this string of numbers and letters. It's the parser which realizes that first thing is name, first line is name, observation date, MACB, etc. It's the parser which says that, okay, when I read M101 on the next line, it must correspond to name, and this particular date must correspond to the observation date, and so on. So it is an intelligent reader or writer of data in some structured form. Okay, maybe a table, it may be a binary blob, and so on. So it's the parser is which parses it, breaks it up into smaller units, and figures out its inherent data structure. And it does it quite automatically. See, remember when we read the file, we didn't specify that there are so many rows, there are so many columns. First column is a string, second column is a date, third column is a float, and so on. We didn't specify anything. We just said, here's a file, read it. The parser is the code that has that intelligence to figure out that something is a float and something is a string, and so on. Right. Okay, so let me go now to the thing. Okay, how to identify any missing values if those are there in the data catalog? Okay, so this is a really difficult problem. Okay, so for example, if the data are missing, they're not available, then in some catalogs there will be nothing there, just space. In some catalogs, there will be some number like -99 or -999 indicating missing data. In some places, there'll be some dash symbol or something else. So obviously, to build a parser that will correctly interpret this is very difficult. The astropy.io.ascii parser, which is used by astropy.table while handling the ASCII files, is quite sophisticated, but it can fail. So there is no foolproof way of identifying what the missing values are if those are there in your catalog automatically. So for example, if you have -99 later on, indicating a missing value in your catalog, and you know that in advance, if you specify that to the read, that can handle it, or after you read it, you can go through your rows and do a numpy.where or some such other structure to eliminate those invalid values, or you can even convert them into masked values so that they are not actually used in any computation. All of these modules play nicely with each other, NumPy, AstroPy, SciPy, etc. So you can easily go from one module to another without any problem. Okay. There's some new question. Can you please elaborate ASCII files? ASCII files are files in the format that only ASCII characters are used. So there was an American standard for information interchange called ASCII, defined many years ago. Though basically consists of all capital letters, small letters, numbers, all the special symbols like comma and exclamation mark and so on. There are only 255 ASCII characters. And when we write a Python program, you will notice that there are very few non-ASCII characters. So that's the meaning of ASCII. How to identify any missing values that we have seen. It's a difficult problem. Can you suggest some statistical and mathematical methods, resources, or books? Okay, so this is a bit tricky, but I would suggest if you want a book, look at the book by Langtangen that I recommended. That will give you some inkling on how to use mathematical methods. Now, this mathematical methods is a very vast subject, as all of you know. So it's possible that there will not be all the functionality that you need will not be there in one module like Scipy. Sometimes you will have to go to some other module for that added functionality. But the basic functionality, for example, solving systems of equations or solving ordinary differential equations numerically using various algorithms, things like root finding and so on, all of those finding maxima and minima and things like that, those are there in Scipy in one form or another. Books I've already mentioned, the book by Langtangen, but I'm sure there are more. Okay, if value at first row and second column given, how to find the corresponding value at first row and fifth column? Okay, that's not a problem. I mean, you know what the column names are. So you just specify, like I've shown in some of the examples. Okay. I have installed Astropy and AstroQuery modules on my computer. Will I need to install anything more? I don't think so, right? Beyond, so obviously you must have installed NumPy and Scipy, because without Astropy has dependency on them. So if NumPy is not installed, Astropy will simply not install. You have to install NumPy first. So for the purposes of this course, I don't think you need any additional modules. Obviously, as you continue down your journey in Python, at some point you may need to install some more modules. If my data set has asymmetric error bars, what kind of curve fitting is available? Okay, so I am not sure of the exact answer to this question, but I think the minimizers that are available in scipy.optimize might be able to weight your data using this asymmetric error bars. Certainly, they do chi-square fitting, so they can handle error bars correctly. But asymmetric error bars is a more difficult problem. I'm not sure whether it can be handled in scipy.optimize, but you can check there. Will we be discussing some examples on plotting using astronomical data from such tables? Yes, maybe one or two examples, but not really in detail. See, remember, I have told you how to plot data given a NumPy array, and it is absolutely trivial. In fact, with images, with tables, also you can plot a column, one column against another column quite trivially, because I should probably mention that when you extract something, when you say remember when we accessed certain objects, like for example, subsection row 2, right? It'll give you the whole row 2. Subsection column is equal to demo table name and MACB. Okay. So this is an object whose columns can be plotted. You can check whether you can do tuple unpacking here, whether you can say name, comma, MACB is equal to this. If that works, then you already have two NumPy arrays. And then you can just plot them, plot name, comma, MACD or whatever it is. So we don't need to go on into great detail. There is nothing special about plotting astronomical data and non-astronomical data. It's the same thing, right? They're both arrays of numbers. You want to plot them. So I will not be giving you exact details, but when you do the assignment 2, you will have to make plots of the data that you read from astronomical tables or astronomical images. You will have to do that. So assignment 2 is designed for that. So when we have the next tutorial discussion, at that point, all of that will be shown. But again, you're encouraged to take the first steps of trying to solve as many questions in assignment 2 as possible, so that we in the tutorial you learn even further beyond what you have tried yourself. On the other hand, if in the assignment you take the attitude that I'll just wait for the assignment solution to come, then you will learn less. So therefore, I strongly urge you, all of you, to discuss, try to solve the assignment. Subsectioning, can you elaborate the third line? Okay, so we are on subsectioning tables. So what do you think this is going to do? It's going to create a subsection of rows where it is going to pick up the second row. Remember, starts with 0, and then it's going to put the 6th row and the 4th row. So you've altered the ordering of the rows by doing this. It's only going to contain 3 rows in your table, which is called subsection row 2. Right here also you're going to have exactly 3 rows, but then the order of those rows will be preserved. Remember here, if you swap the order of MACD and name, then the table will have this order swap. Will you discuss how to read FITS file? Absolutely, yes. FITS files are coming in the next class.